let's see how the E2 elimination affects ring systems. So we'll start with a really simple one. So here I have a chair conformation for cyclohexane, and I haven't drawn in my bonds yet. So remember, you start right here at carbon 1, and you always start up and axial. So right there, I'm going to go up, and then you alternate when you go to carbon 2, you're going to go down. So I have two axial substituents in there. And I'm not going to draw the rest of the molecule because we're only going to focus in on this right side. So next you do equatorial, and since you started up for axial, you're going to go down. So down equatorial, and then you're going to alternate. So up equatorial. So that's all we're going to need to draw for this little example here. And we're going to go ahead and put a chlorine up at carbon 1. Okay, so we're going to put a chlorine up at carbon 1. And if you can imagine, everything else is being hydrogen on this ring. So we're going to have chlorocyclohexane, and we're going to react chlorocyclohexane with sodium ethoxide. Right? So sodium ethoxide will be our base for this reaction. And remember, when you're doing an E2 elimination reaction, you must have an anti-periplanar conformation. So you need to look for the anti-periplanar hydrogens on your beta carbons here. So if we first find our alpha carbon, right, it's the one attached to our chlorine, so this is our alpha carbon, and our beta carbon would be the one right next door here, so this is my beta carbon. Now, where is my hydrogen that's anti-periplanar to that chlorine? Well, on my beta carbon, it's the one that's down here, right? There's a hydrogen going down, and that's in the same plane as the chlorine. So this is the proton that's going to participate in this reaction. Notice how chlorine as your leaving group must be axial for an anti-periplanar conformation. And one more thing you should note here, this looks just like a sawhorse projection, as we saw in the last two videos when we're drawing our mechanism, right? So if I try to highlight all of the bonds here, right, you can see that it actually looks just like a sawhorse projection, right? So hopefully you can see that sawhorse projection in there. And when we were drawing our product, right, what we did was we took our sodium ethoxide as our base, takes this proton, right? These electrons are going to move in here to form a double bond between your alpha and your beta protons, and then these electrons are going to kick off onto your leaving group, which is chlorine in the axial position. So you end up with a double bond forming between carbon 1 and carbon 2. So wherever you want to put that on your molecule here, it doesn't really matter. And you make cyclohexene out of this. So that's the idea. Look for the anti-periplanar conformation with your leaving group axial. Let's do a harder one, right? Let's do Neomenthol Chloride. And so to save time, I've gone ahead and put in here your two chair conformations for Neomenthol Chloride. And in an earlier video, I showed you how to actually draw these. So you can check the earlier video for that. For right now, we're most concerned with which one of these two conformations is the most stable, right? So again, that's also from the earlier video. We saw that you want to put your bulkiest groups equatorial, because if you put your bulkier groups equatorial, that's more stable, there's less steric hindrance. So that would be the conformation on the right here. So I have my isopropyl group over here off to the side, equatorial, methyl group equatorial, and this puts my chlorine axial. So this would be the major conformation, and that makes this one over here minor. And the reason why this one over here on the left is minor is because your bulky groups, your methyl group and your isopropyl group, are axial, and that destabilizes this conformation somewhat. So major conformation is on the right. And that's one we're going to focus on because that's one where our chlorine is axial. So our leaving group needs to be axial here. So we identify our alpha carbon, right? So this would be my alpha carbon right here. And so let me go ahead and number these. I think it'll make it easier, right? So remember, if let's say this is carbon 1, this is carbon 2, carbon 3, and carbon 4, then this would be carbon 1, this would be carbon 2, this would be carbon 3, and then this would be carbon 4. So my possible beta carbons would be at 1 and 3, right? So 1 and 3 would be the two possibilities for my beta carbons. And lucky for us, there's a hydrogen at both of those places, right? So if you look closely there, you can see that either one of those hydrogens is anti-periplanar with that chlorine. So either one of those protons could participate in the elimination reaction. So if the base came along, right, if the sodium ethoxide came along, let's go ahead and draw it out here. Let's go ahead and draw out the molecule. So sodium ethoxide negatively charged. If that came along and grabbed this proton, right, for your mechanism, the electrons in here would move in to form your double bond as your chlorine leaves. So let's go ahead and draw what we would get if that is the reaction that occurred. So let's get some more room here. So the double bond is going to form between the 2 and the 3 position, right? So if I draw my product like this, right, and I make my isopropyl group coming up at me, right, and then carbon 2 and carbon 3, all right, if I number my chain here, if I number my ring, 1, 2, 3, and 4, the double bond forms between the 2 and the 3 positions, so between the 2 and the 3 position. And then I also have a methyl group going down at carbon 4, right, so a methyl group going down at carbon 4. So that's one possible product. So remember, I have this other proton over here, right? So my base could take this proton. Okay, it's also anti-periplanar. If that happens, these electrons would move in here to form a double bond between 1 and 2, and then your electrons would kick off onto your leaving group in the axial position there. So that's a possibility as well. What would we get? What would we get if that happens? So let's go ahead and draw our product here. So once again, we have an isopropyl group at carbon 1. Now this time there's no stereochemistry associated with your isopropyl group, and that's because your double bond forms between carbon 1 and carbon 2. So let me go ahead and number my carbons here once again, 1, 2, 3, and 4. Your double bond forms between carbon 1 and carbon 2 because this hydrogen, this proton, is leaving in this mechanism, and that changes the hybridization state of your beta carbon from sp3 hybridized to sp2 hybridized, right? So this carbon right here, right, is now sp2 hybridized. Everything's flat and planar, so there's no more stereochemistry with it. So that's why I didn't draw a dash there. I just drew a straight line. There is stereochemistry associated with the methyl group, right? It's still going away from us like that. So we have two different possibilities for our products here. Which one of these two is going to be the major product? Well, to think about the stability of the alkene, right? So over here on the left, we have a di-substituted alkene, right? A di-substituted. So right here across our double bond, there are 2 R groups. And for the example on the right, across our double bond, there's actually 3 R groups. So on the right, it's actually a tri-substituted alkene, and that makes this the major product because we know tri-substituted alkenes are the most stable ones, and then the di-substituted one will be the minor product. So for this reaction, 2 possible products, and it's all about being able to draw your chair conformations and understand the anti-periplanar conformation relationship between your proton and your leaving group. Let's do one more. Okay, so menthol chloride, very similar to neomenthol chloride. Okay, so let's go ahead and look at the 2 chair conformations for menthol chloride. Once again, to save time, I've already drawn them from you, and go back and look at the previous video for an explanation of how I did it. So for this situation, we look at these 2 conformations. Which one of these 2 is the most stable one? Right. So once again, we're looking for putting your bulky groups axial, and so once again, isopropyl group. Bulky group's equatorial. So here our isopropyl group is equatorial and our methyl group is equatorial, and actually our chlorine is equatorial. So everything is equatorial here. That's the most stable conformation, right? So this is the major conformation, and that makes this one over here the minor conformation. So this one's minor. That's because all of our bulky groups, everything is axial, right? The methyl group is axial, the chlorine is axial, and the isopropyl group is axial. So, which one of these 2 conformations is going to be the one that's important for our mechanism? Well, our leaving group needs to be axial. So, the minor conformation is where our leaving group is axial for this one. So, if we're identifying our alpha carbon, right, this is our alpha carbon. And if we're looking for beta protons, right, well, this is a possibility for beta. And this is a possibility for beta. Let's look at the one on the right first. The isopropyl group is going up. That obviously can't participate in the mechanism. Even though we have a hydrogen over here, right, this proton is not anti-periplanar. So this beta carbon over here is not going to participate in any kind of reaction. This beta carbon, on the other hand, one of these is hydrogen that's in an anti-periplanar conformation with our chlorine, with our leaving group. And so this is going to be the only proton that's going to participate in this mechanism. So when we draw our base, right, our sodium ethoxide anion comes along. So the negatively charged ethoxide anion is going to take this proton, which leaves these electrons behind to form a bond here as your chlorine leaves. Okay, so once again, if we were to number our carbons, right, let's say we made our isopropyl 1, 2, 3, and 4. I'd make this 1, 2, 3, and 4. So the double bond is going to form between carbons 2 and 3. So if we're going to go ahead and draw that, right, draw the product, showing our double bond forming between carbons 2 and 3. So we have an isopropyl group at carbon 1 coming out at us. So we're going to go ahead and draw this. It's going up relative to the plane. And let's go ahead and number this guy as well. So we have carbon 1, 2, 3, and 4. We know the double bond is going to form between carbon 2 and 3. So double bond forms between carbon 2 and 3. And then we have our methyl group down at carbon 4. So this will be our product. So this is our only product because there's only one anti-periplanar proton for this mechanism. So we have two alkyl halides. Each one can react via an E2 elimination reaction. Now the question is, which one of these two alkyl halides that we studied is going to react the fastest? And the answer has to do with the stability of the conformations. Right? For menthol chloride, for this example, the chlorine in the axial position is only present when it's in the minor conformation. So most of the time the molecule is going to spend in the major conformation. So this alkyl halide will be slow to an E2 elimination because most of the time the chlorine is not in the correct conformation. That's in contrast to Neomenthol Chloride, right? So if we go back up here to Neomenthol Chloride, right? For Neomenthol Chloride, most of the time is spent in this conformation, the major conformation, and in this conformation your leaving group is axial already. So this makes Neomenthol Chloride much faster for an E2 elimination reaction. So by a factor of somewhere around 200 times. So it's approximately 200 times faster to an E2 elimination than menthol chloride. And again, it all has to do with the conformations and which conformation is the most stable. So, as you've seen, the anti-periplanar relationship is the most important thing to understand when you're doing E2 mechanisms.